Okay, well, welcome everyone to another TCS Plus talk. Today we're very lucky to have Zeyong Lee from National University of Singapore, who will tell us about simple circuit lower bounds via algorithms for range avoidance problem. So now before we begin, I do want to encourage everyone to keep their cameras on. It really gives Zeyong some visual feedback and makes the talk much more pleasant for him. And please feel free to unmute yourself and ask questions throughout the talk. The talk is being recorded, so we'll post it on our website, but we'll stick around at the end of the talk and have an unrecorded session where we can just hang out with Zeyong and ask any other questions. Um, okay, so with that being said, I'll pass the floor over to Zeyong Lee. And yeah, please take it away.
Yeah, thanks for the introduction. So hi everyone, thanks for coming up. And this is Zeyong from National University of Singapore. Today I'll be talking about simple circuit lower bounds via algorithms for range avoidance problem. And I actually have like a slightly simpler title or agenda for the talk, which simply says solve range avoidance and prove circuit lower bound. So let me start by motivating the study of circuit lower bound. So at a very high level, it studies the difference between uniform and non-uniform computation. So it studies the difference between, say, Turing machine versus circuit families. And there will be very good consequences if we can prove very strong circuit lower bounds. For example, if we are able to show that NP is not in P/poly, then straight away we show that P is not equals to NP. And I hope everyone will be happy, of course, for that. And if we are slightly less ambitious, if we are able to show that E does not have circuits of size 2 to the small of n, then we obtain de-randomizations. And this is the well-known result by Impagliazzo and Wickerson. And by the way, in case you haven't heard about it, every Wickerson just received the Turing Award a few hours ago. And over here, E stands for deterministic 2 to the order n time. So throughout the talk, whenever the letter E shows up, it typically represents the exponential time of some polynomial complexity class, like the exponential time version of some polynomial complexity class. We'll see more of it later on. Right, so what was known about circuit lower bounds? Since if we can prove strong circuit lower bound, we have good consequences. And I would like to bring down the expectation by quoting Ara Barat, which says that circuit lower bound was complexity theory's Waterloo, in the sense that we really do not know much about circuit lower bounds. So what was known exactly from a probabilistic argument, we can show that if we just pick a random function that maps n bits to 1 bit, and with high probability over the choice, the random function that we pick is going to require exponential side circuits. This is simply because there are just way too many functions, and therefore a random function has to require high circuit complexity. But for the explicit functions that we can show, in 1982, Kanan shows that sigma 3e cannot be computed by circuit families of size 2 to the n over n. Here, sigma 3e means the exponential version of the third level of the polynomial hierarchy. And after about 20 years, Milterson, Vinod Chandran, and Watanabe improved the results by showing that e to the sigma 2 cannot be computed by circuit families of size 2 to the n over n. So this is like, you can think of it as like half of the step on the polynomial, on the exponential hierarchy. And that's basically it for what we know about circuit lower bounds of exponential size. And if we are happy to relax the requirement on the size of the circuit lower bound, we know a little bit more results. So over here, I have a list of complexity classes sorted from small to large. So on the left, we have e to the NP, which is the exponential version of p to the NP. So there's an algorithm that's encrypted with a NP oracle. And in the middle, we have ZPE to the NP, which is the exponential version of ZPP to the NP. And likewise, we have sigma 2e and e to the sigma 2. And there's also a funny class S2e sitting here. So for the purpose of this talk, don't worry too much about this class. It suffices to know that it sits in between e to the NP and ZPE to the NP. So what kind of circuit lower bounds do we know about this?
Sorry, just a second.
So what kind of circuit lower bound do we know about this? So from the previous slides, we know that for this class, e to the sigma 2, we have 2 to the n over n circuit lower bound. So I have a happy face here. And for the classes in the middle, something called known as the half exponential circuit lower bound is known, in the sense that if you apply the function twice, you get 2 to the n. So it's not quite optimum, but it's still something. And this type of circuit lower bound is typically obtained via the Karp-Lipton type argument. And for e to the NP, the best circuit lower bound we know, it's linear in end. And it's clearly not very satisfactory, and I have a sad face here. And this is actually a fairly recent result in 2022 by Jiatu Li and Tianqi Yang. So that's the status. And just a side remark, if we believe in some strong derandomization assumption, these three classes here all collapses to e to the NP. So there's something to hope for, like we could probably get stronger circuit lower bounds for e to the NP. So as I mentioned earlier, the status for exponential size circuit lower bound was stagnant for about 2 decades until very recently. Chen, Hirahara, and Ren, they show that S2E up to 1 bit of advice cannot be computed by circuit families of 2 to the n over n. So as a reminder, the complexity class S2E sits here in between e to the NP and ZP to the NP. And they achieve this by giving a single valued FS2P algorithm for the range avoidance problem. And the algorithm works for infinitely many input size n. So I'll talk about single valued and range avoidance later. And here the letter F stands for functional, which indicates that we are actually solving a search problem. So usually for a typical complexity class, we discuss about decision problems. So here we use an extra letter F to indicate that we're actually using the algorithm to solve a search problem. So what's a single value algorithm? At a very high level, you can think of it as algorithm is single value if a computational path of the algorithm is considered correct only when it outputs a canonical solution. It's fine if it doesn't quite make sense at the moment, so I will have examples. So for example, let's consider the following task. Say the goal was to generate an n-bit prime number. And this task has a very simple randomized algorithm. So I can simply just sample an n-bit number, and I use whatever primality test algorithm that I have to test if the n-bit number I sampled is a prime number. If it's a prime number, I output it. If it isn't, I will try again. And because prime is dense, with good probability, I'll hit a prime number and I'll output it. So this is an algorithm for generating an n-bit prime number, but it's not single valued, because each time you run the algorithm, you are using a fresh set of randomness, and the prime number that you are going to generate at the end, it's going to be different almost always. And for a single value algorithm to work in this context, you really want the algorithm to generate the same prime number most of the time. In the discussion of randomized algorithm, this is also considered as pseudo-deterministic algorithms, in the sense that if there is a bounded observer observing the behavior of the algorithm, the observer would think of the algorithm as a deterministic algorithm. And just a side note, the task of pseudo-deterministically generating a prime number is recently resolved, and Halin actually has a very nice talk on this topic also at TCS Plus. And next, what's the range avoidance problem? So this problem was introduced in Kleinberg, Cotton, Mitropolsky, and Papadimitriad in 2021. So it has a very simple and clean definition. The input is a circuit C that maps a n-bit string to an n+1 bit string. And the output is a n+1 bit string Y that's a non-image of the circuit C. So in other words, for any input X that fits into the circuit C, it shouldn't evaluate to Y. And if you think about it, this problem can be trivially solved in FZPP to the NP. So it means that you have a randomized algorithm and you also have access to an NP oracle. So similar to what we did in the prime generation case, I can just uniformly sample a n+1 bit string, and I make use of the NP oracle to check that if the string that I generated has a pre-image. If it has a pre-image, then I try again. If it doesn't, I output it. And because we are searching in a space of 2 to the n+1, and there are at most 2 to the n images, so with probably at least 2, I will succeed. And it was shown by Cotton that the range avoidance problem defined above actually captures optimum explicit constructions for many important combinatorial objects. These objects typically has a construction that's randomized, proved via the union bound. So examples include Ramsey graphs, rigid matrices, two-source extractors, and so on. And among them, the one that's particularly relevant for us would be the hard truth table. And let me just give another remark that this problem actually also has connections to bounded arithmetics. But because of time constraint, I'm not going to elaborate on that part. So just to give an intuition behind why this problem was related to constructions of all those combinatorial objects. So I've here a picture of, say, imagine this is what happens when the circuit, when we apply the circuit. So it maps the domain to its range, and there's a much bigger codomain. And suppose that the circuit C works in a way that it maps all the bad combinatorial objects into its range. Now, by definition of the range avoidance, I'm going to obtain a solution in something outside the range, and which guarantees that whatever that I obtain is going to be a good object. So therefore, if you can solve range avoidance, you will figure out how to construct all those combinatorial objects. And as a more concrete and relevant example, let's see how solving range avoidance brings us circuit lower bound. So in particular, we are going to use this circuit called the truth table generator circuit. So indexed by TT. And this circuit takes in as input another circuit that has n bit input and 1 bit output, and it evaluates the circuit on all possible inputs and obtains the truth table of the circuit and outputs the truth table. So again, he takes in as an input a circuit, outputs the truth table of the circuit. And the size of the input that it can allow to take is roughly 2 to the n over n, because you want to make sure that this TT circuit is expanding so that it's a valid range avoidance instance. And from here, immediately, if we run range avoidance on this truth table generator circuit, we obtain a truth table. And moreover, by definition, this truth table has to have a very high circuit complexity, because every truth table which has small circuit complexity will fall in the range of TT. So now let's see how a single value algorithm for range avoidance implies very strong circuit lower bound. So suppose for now we have a single value f sigma 2 p algorithm for range avoidance. So think of it as the search version of sigma 2, and sigma 2 is like the second level of the polynomial hierarchy. And if we just solve a void on the input TT, the truth table generating circuit, we can obtain a hard truth table F that's 2 to the n bits. And we use F to define the hard language L on n-bit inputs. And by definition of of running range avoidance on TT, this hard language L cannot be computed by any circuits of size 2 to the n over n. On the other hand, this language can actually be decided in sigma 2e because we can just run the f sigma 2e algorithm to obtain the truth table F and look at the correct position of the truth table, which tells you whether you should accept or reject input to input or a string, whether the string is in the language L or not in the language L. And here we lift it from f sigma 2p to f sigma 2e because this truth table generator has size 2 to the order n. So if we measure in terms of the small n, this takes time exponential in n. And that's like the big picture for how if we start with a single value algorithm, we can find a hard language that has high circuit complexity, and it's also contained in whatever complexity class that we wish for. And at this place, it's where we require the single value requirement. Because we are defining the language, we want to make sure that every time we try to decide the language, we are using the same truth table. So we wish to generate the truth table consistently. So coming back to the results, as I mentioned earlier, in the recent breakthrough by CHR, they show that S2E with 1 bit of advice has very high circuit complexity. And this was done by giving a single value algorithm that works for infinitely many input size n. And to achieve this, they applied a very careful iterative win-win argument so that on infinitely many input size n, they will succeed on those input size. And what happens in our result is that we observe that we can actually just win. So in the sense that for every input size n, we are able to solve range avoidance. So we don't have to go through the iterative win-win argument. And as a result, we are able to get rid of the 1 bit of advice in the circuit lower bound. Because this 1 bit of advice is used to indicate which input size is the good input size. Because the algorithm only works for some input size and not all input size. And because now our algorithm works for all input size n, we no longer need the extra 1 bit of advice. And so here is our result. And let me try to brag a little bit more about it by increasing the font size. But besides that, our result has a little bit has some nice properties. So first of all, the circuit lower bound that we construct is explicit, in the sense that we constructed a explicit language that has high circuit complexity, and the language falls in the complexity class S2E. Secondly, the circuit lower bound we obtain is called almost everywhere, in the sense that for all input size n, the language is hard. So even if we relax the circuit, relax the requirement and allow the circuit family to only evaluate the language on some input size, there is no circuit family that can do that. So in this sense, this is a strictly stronger lower bound result. And thirdly, the circuit lower bound, that the size that we obtain, 2 to the n over n, is near maximum. This is because if we slightly increase this size, one can show that every function can be implemented by some circuit family with slightly larger size than 2 to the n over n. So this is like the largest possible that one could hope for. And lastly, our result relativizes. So if both sides are encrypted with any oracle, the result still holds. And depending on where you stand, this may or may not be a good property, but it just relativizes. So this is roughly what I have for the first half. So I would like to pause for a short while and see if there are questions before I go to the second half. Okay, so I guess I will proceed. So for the second half, we will see how we actually solve range avoidance. So as an appetizer, I will show you a F sigma 2p algorithm for avoid without asking for the single value requirement. So, and before that, let me just give the definition of what's a F sigma 2p algorithm. So similar to what you usually see for the definition for sigma 2, there should exist some pi1 such that for pi2, there is some polynomial time verifier that outputs a non-image of the circuit C. And there's a second branch where for all pi1, there should exist some pi2 such that the verifier either outputs a non-image or he gives up and outputs bottom. And notice that in both cases, the verifier never outputs a image. So in this sense, it never makes an error. And it might be slightly easier or more intuitive to think of it as a two-prover system, and with the verifier sitting in the middle. And the first prover sends in pi1. The second prover, after seeing pi1, sends in pi2 to the verifier. And what does the verifier do? So in this case, the verifier would simply check, is pi2 a pre-image of pi1? If pi2 is a pre-image, then I should not output pi1, so I should output bottom. Otherwise, if pi2 is not a pre-image, and with the knowledge that the second prover is all-powerful, I should think of it as the pi1 actually is a non-image. Therefore, I should try to, the verifier would output pi1. So here, think of the first verifier as proposing some non-image pi1 as the first prover. And the second prover would try to refute bad pi1s. If whatever pi1 that's given is an image, he'll try to find a pre-image for that. So the definition of this of the F sigma 2p algorithm actually corresponds to a case where one of the prover is malicious. So in the first case, think of the first prover is honest and the second prover is malicious, which corresponds to this point, the first point. So in this case, the honest prover sends in some actual non-image pi1. And because the pi1 is a non-image, the malicious prover is not able to find a pre-image for pi1. And therefore, my verifier will correctly output pi1 because there is no way for the malicious prover to find a pre-image. And this corresponds to the first line of the definition. And in the other case, if the first prover is malicious and the second prover is honest, so now think of the first prover, him being malicious sends me some pi1, which is an image of C. So it has some pre-image. Now the second prover, he's nice, he's honest, he'll try to protect me from being fooled by the first prover. He will find a pre-image to the pi1 that I received. So I can, as a verifier, I can check that the pi2 that I received is actually a pre-image of the pi1. Then I realize that the first prover is being malicious, then I should just output bottom. So that corresponds to the two cases in the definition of F sigma 2p. And now if we just throw in the requirement that the algorithm should be single valued, here is how the definition changes. So before, we have that it either outputs a non-image or it outputs bottom. Now, whenever the verifier outputs something, if it's not bottom, it should be some fixed string YC, which is some canonical non-image of the circuit. So now I'm not happy with any non-image. I only want a specific non-image. And that's exactly what it means to be single valued. There is some consistency happening here. And with this definition in mind, one can immediately see that whatever protocol we have just now does not work anymore. Because if the first prover, whenever the first prover sends in a non-image, the verifier will output it. And now if he sends in different non-images, the verifier will output different outputs, which violates the single value requirement. Okay? So here's the end of the appetizer. Let's go on to actually build a single valued algorithm for range avoidance. And as a starting point, we'll start with a quote-unquote naive algorithm from Cotton. So from now on, we are going to work with circuits that match from n bits to 2n bits. So just now we have it mapping from n to n plus 1 bits, but they are equivalent up to a certain extent, so don't worry about that part. So for now, we'll try to find a non-image for circuits C that maps n bit to 2n bits. And we are going to make use of an NP oracle. And now let's consider a perfect binary tree. And this is actually the GGM tree, where GGM stands for go right, go Wasser, Macaulay. And each of the vertex in the tree, in the binary tree, we are going to give him an n-bit string. And at the leaf level, we are going to fill in all possible 2n-bit strings. So what does this mean? Every vertex is an n-bit string, so I need two vertices to form a 2n-bit strings. And I'm going to fill them with all possible 2n-bit strings. So all 0, 1, 2, 3 until all possible 2 to the 2n possibilities. And as a consequence, this tree is going to be humongous. It's going to take the size of 2 to the 2n, but don't worry about this for now. We'll fix that issue towards the end. And here's what the algorithm is going to do. It's going to invert the vertices using the help of the NP oracle, in the sense that in the first time step, he's going to look at these 3 vertices and treat these 2 vertices as the output of the circuit and find a pre-image of these 2 vertices. So he will try to find some value such that if you apply the circuit on this value, you exactly get whatever you have at as its children's. And if there are more than that, we'll try to get the lexicographically first string that's the preimage. So in other words, for all string that's lexicographically smaller, you shouldn't be the preimage because I will try to always use the lexicographically first preimage and fill it in this vertex. Okay, so and this lexicographically first requirement can be done with the help of an empirical. And now let's just keep repeating this procedure from left to right and from bottom to top. So in the second time step, I'm trying to revert this vertex, find a preimage of these two vertices. And time step 3, I'm going to invert this. And at some point, I'm going to hit something that I will fail to find a preimage. Because remember that at the beginning, we fill the leaf level with all possible strings. So by definition, some of the strings must be a non-image of the circuit. And when I hit one of those, I will fail to invert them. And when this happens, I just put label bottom to this vertex. And at this point, I also label bottom to all the remaining vertex that I haven't touched yet. So now I have a tree that's labeled either with bottom or with some n-bit number. And I claim that this tree is very useful. So here are some properties on why it's useful. So first of all, this tree is unique in the sense that it's generated from executing the algorithm. And the algorithm itself is deterministic. Every step we run is fully deterministic. So this tree that it's generated is unique. And second, somewhere in the tree, it contains a solution to the range avoidance. In particular, the solution is stored here. It's where we first find a place where we fail to invert. And because of these two properties, it's single valued. So if I can always obtain this tree, then I can always obtain the same solution to the range avoidance. And more importantly, it has a locally verifiable property. What does this mean? It means that if someone gives me a tree and he claims that the tree was exactly the tree that generated by running the Cotton's algorithm, can I verify that? How do I verify that? So I can verify that in the sense that for any time step t, I can verify the t step of the algorithm by reading only at most 3 vertices. So for example, when t is equals to 1, recall that what we do was just invert the vertices and figure out what's the value at this vertex. So we just need to check that this vertex is actually a preimage of this two. And also there is this extra lexicographical first requirement where all smaller values shouldn't be a preimage. But what's important is that I only need to read 3 vertices even though the tree is humongous. So for me to verify the t step, I only need 3 vertices. And that's why we call this locally verifiable. And this is true for all time steps. And if we want to check that the whole tree, if we want to check that the whole tree is correct, it's the right tree that's generated from executing the algorithm, we can just use a single for all t quantifier to do the check for us. And notice that I have 2 for all quantifiers here, so I can merge them into a single for all quantifier. So in this sense, this whole tree is verifiable using only 1 single for all quantifier. So now with this in mind, let me try to give a single valued F sigma 2p algorithm for a void. So the first prover gives me the tree, gives the verifier the tree. The second prover gives a time step t and some auxiliary information that's useful for the verification. And the claim, he tried to claim that the T step in the given tree is wrong. It's not the right behavior of the actual, the unique tree that you will obtain from executing Cotton's algorithm. And the verifier sitting in the middle just need to verify is the T step correctly executed. He might need to use the auxiliary information X, but fundamentally he's verifying a single step of the execution. And because the correct tree can be verified using the for all quantifier, so this would work, except one issue. The tree here is too large. So we started off with an exponential size tree, and we are trying to and we are trying to give a sigma 2p algorithm which should be polynomial in size. So the message should be polynomial in size. So the tree is just too large, and he cannot just send in the whole tree. So to do that, we will try to compress the tree. And towards that, we are going to look at a slightly different tree, in the sense that when we invert the vertices one by one, we are going to change the order on how we invert the vertices. So at this point, we are going to use this thing called a post-order traversal, which basically means that if you have traversed the two children of a vertex, then immediately after that, you should traverse the vertex. And so here is what we are going to do. We again invert this. Now, instead of going to the right, because these two children of this vertex are now traversed, we'll immediately go to this vertex and we'll try to invert it. And then we continue until we hit something that we fail to invert. And likewise, we still label the rest of the vertices bottom. Now, at this point, I claim that this tree can be compressed. This is because you can now decompose them into order n many subtrees. This is a proof by picture, but if you want a different intuition, you can think of it as you cannot have subtrees that has the same height. Because if you have two subtrees that have the same height, you should intuitively go to the parents of these two subtrees and try to merge them into a single tree. That's a very vague intuition, but if you just follow the post-order traversal a little bit, it should be clear that you should be able to decompose this big tree into order n many subtrees. And these subtrees, they will have different heights. And that's also how you prove that there are at most order n many subtrees. And with that, what's more important is that for every single subtree, the value at the root uniquely determines everything in the subtree. Because if you think about it, if you want to know whatever value is here, you just need to apply the circuit C on the first vertex, and you immediately know the value of these two vertices. And you can repeat this procedure, and you get the values lower. So if you are curious about a particular value, say this guy, I can just walk down the tree from the root of this subtree and apply the circuit C at every step, and I can obtain the value of this vertex. So because of this property, we only need to remember the values at the roots. So this is the compressed tree, or the witness that we are caring for. So we'll just remember whatever value that we have at the roots of these subtrees. And because there are order n subtrees, the total size that we need to remember is polynomial in n. And so now we have this property that there exists some small witness such that for all time step t, the correct tree would correctly execute the t step of the algorithm. And now I can complete the single value algorithm. The first prover simply sends in the compressed tree. And again, the second prover sends in a time step t and some auxiliary information. And the verifier in the middle verifies if the t step is correct. If the t-stack is correct, he will try to read whatever the solution is stored in the compressed tree and output it. And if the t-step is incorrect, he will just output bottom. And that's the end of the algorithm. And so, yeah, before I go to conclusions, maybe I'll stop here for a while and in case there is any questions. Okay. So now let me try to conclude with a few corollaries. We have shown that we can have explicit almost everywhere near maximum circuit lower bounds. This is the picture from before. And now, because of our results, for all the classes in the middle, we can also obtain 2 to the n over n circuit lower bounds. And I turn the neutral phase into a happy phase. And secondly, because we have a single valued FZPP algorithm for range avoidance, it implies that we can have pseudo-deterministic FZPP to the NP constructions for all of these important combinatorial objects. So here means that you are a randomized algorithm, you have access to an NP oracle, then you can consistently generate the same object, even though you are using fresh randomness every time. And finally, a few open problems or interesting directions that to look into. So a natural open problem to ask for is that can we push the result further and obtain circuit lower bounds for smaller classes? For example, e to the NP or e to the promised MA. And I have a small warning here, which is that there exists relativization barriers for e to the NP if you want to show circuit lower bounds for e to the NP. And recall that our proof above fully relativizes, so it might be interesting to see how one can get around the relativization barrier if one is really trying to push that to e to the NP. And the second very interesting observation by Hanlin is that our proof actually implicitly induces a total order among all witness strings. And this property was not used in our proof. So it's actually interesting to see that if this extra property can buy us something more. And lastly, in a very recent follow-up work, me and my co-author, we look into this oblivious complexity class called O2P. Don't worry about its exact definition, but it's somewhat interesting in the sense that this class simultaneously emits fixed polynomial circuit lower bound, and it's also contained in P/poly. So in this sense, it's sandwiched between circuit families of different sizes, and which makes it interesting to think about, at least to me. And so, and it might also be interesting to consider its relationship with P to the NP. And I think this might be a possible way to attack circuit lower bounds for P to the NP or E to the NP. And yeah, that's all I have. Thank you for your attention, and questions are welcome.
Okay. Do we have any questions for Zeyong Lee? So I guess I have a question, Zeyong.
Yeah.
Could you maybe say a sentence of why what was the previous work that they were doing, how they were not getting this for every n, or
Right, so let me see. So sorry, 1 second. Right, so they work with this version of the algorithm. So, and they treat the tree as like a very long string. And so they applied the iterative Riemann argument in the sense that they consider two scenarios. If this string has a small circuit, evaluating it. If yes, then you have a short witness, similar to what we have here. So that's one of the win. And if no, you have a string that has high circuit complexity, because you assume that you are in the other branch. The string has high circuit complexity. So now they will use this string to fill in the bottom level, to fill in the leaf level of the tree for a larger n. So by doing this, they need to work with a different input size n, and over there they can they can make the tree smaller by using a string with high circuit complexity. And by doing this iteratively, at some point you will obtain a high complexity string that's polynomial in the new input size n. And at that point, you succeed. And because of this iterative Riemann argument, you know that at some point, at some input size n, you will win, but you don't win everywhere.
Okay, thanks. So it seems there's a question in the chat. Could you please give some explanation?
So yes,
Be read out loud for the recording.
Yes, so these are witness strings, right? So you can consider a witness string as you can consider the space of all witness strings as in I can have different configurations of the trees, and I take the vertex values, and I can have arbitrary values for them. So that defines different witnesses. Of course, only one of them is a good witness. The rest are not good. And there is a total order in the sense that if you give me two witnesses, there is some comparator that compares which one is better. And also the comparator guarantees that if you give me the right witness, this right witness always wins. Regardless of how you compare with the rest, he's always the better witness. And moreover, what I described as the order, partial order. So it's actually a total order in the sense that consider any two arbitrary witness. Actually, you consider three witness. If the first A is better than B and B is better than C, then you can automatically conclude that A is better than C. So in some sense, you are ordering the set of all possible witnesses in a list. And whichever is on the right is a better witness, whichever is on the left is a worse witness, and you have a comparator that tells you which one is better, which one is worse. And actually the comparator runs in polynomial time.
I see that, thanks.
Okay, so maybe I'll take us offline. We can just hang out with Zeyong. But let's thank Zeyong once again.
Thank you.